After completing this lesson, you should be able to achieve the objectives shown on the slide. By demonstrating competence in BGP, you will be able to configure FortiGate for BGP, monitor and check the status of a BGP communication, and troubleshoot the most common external BGP issues. In this section, you will review BGP and how to configure it on FortiGate. An AS is a set of routers and networks under the same administration. Each AS is identified by a unique number and usually runs an interior gateway protocol such as OSPF or RIP. BGP can serve one of two purposes: eBGP and iBGP. An exterior gateway protocol, EGP, exchanges routing information between autonomous systems. BGP4, which runs in the Internet, is the dominant EGP protocol today. eBGP is typically used when strict control is required over a large number of routes. Two eBGP routers exchange AS path information for destination prefixes or subnets. When two routers start an eBGP communication, the whole BGP routing table is interchanged. After that, only network updates are sent. A BGP speaker or peer is a router that sends and receives BGP routing information. The connection between two BGP peers is called a BGP session. There are three types of autonomous systems. A stub AS handles and routes local traffic only and has only one connection to another AS. One example is a company that is running BGP and has its own AS number and one ISP connection. Multi-homed AS also handles and routes local traffic only, but it has multiple connections to different autonomous systems. One example is a company that is running BGP and has its own AS number and multiple ISP connections. Transit AS handles and routes local traffic as well as traffic that originates and terminates in different autonomous systems, transit traffic. An ISP is an example of a transit AS. When running iBGP, you usually need to configure full mesh peering between all the routers. In large networks, full mesh peering between routers can be difficult to administer and is not scalable. RRs help to reduce the number of iBGP sessions inside an AS. An RR forwards the routes learned from one peer to the other peers. If you configure RRs, you don't need to create a full mesh iBGP network. RRs pass the routing updates to other RRs and border routers within the AS. In a BGP RR configuration, the AS is divided into different clusters that each include an RR and clients. The client routers communicate route updates only to the RR in the cluster. The RR communicates with other RRs and border routers. A FortiGate can be configured as either an RR or client. A BGP router stores the routing information in three logical tables. The RIB-IN table contains all the routing information received from other BGP routers before any filtering. The local RIB table contains that same information after the filtering. The RIB-OUT table contains the BGP routing information selected to advertise to other BGP routers. This slide shows a flowchart that summarizes the BGP process. The BGP router stores the BGP routes it receives from other routers in the RIB-IN table. The BGP router applies a filter, and the resulting routes are stored in the local RIB table. Then the BGP router adds routes that were redistributed from the routing table and applies another filter, outbound. The BGP router advertises the resulting routes. BGP routes traffic based on AS paths. Each AS path includes attributes, which BGP uses to select the best route to each destination. One of the attributes is the AS list, which contains the autonomous systems through which the traffic must pass to reach the destination. There are 4 types of BGP attributes: well-known mandatory, well-known discretionary, optional transitive, which can be passed from one AS to another, optional non-transitive, which can't be passed from one AS to another. This slide shows a list of the BGP attributes and their attribute types that are supported by FortiGate. FortiGate uses some of the attributes during the routing selection process. If all those attributes for multiple routes to the same destination match, and if ECMP is enabled, FortiGate shares the traffic among up to 10 BGP routes. If you don't enable ECMP, FortiGate uses the route that goes to the router with the lowest BGP router ID. There are 3 important things to consider when you implement BGP on FortiGate. First, there are no hard-coded limits. Limitations on the number of neighbors, routes, and policies depend exclusively on the available system memory. Second, by default, FortiGate doesn't originate any prefix. You must enable redistribution or manually indicate the prefixes that FortiGate originates. Third, by default, FortiGate accepts all the prefixes it receives. Optionally, you can filter out or modify some prefixes. By default, FortiGate BGP doesn't advertise prefixes. You can use the redistribution command to configure FortiGate to advertise prefixes. You can redistribute connected and static routes and routes learned from other routing protocols into BGP. Optionally, you can add route maps to filter the prefixes or modify some of their BGP attributes. You can also use the network command to configure FortiGate BGP to advertise prefixes. However, an exact match of the prefix in the network command must be active in the routing table. If the routing table doesn't contain an active route whose destination subnet matches the prefix, FortiGate doesn't advertise the prefix. You can change this behavior by disabling the Network Import Check setting. After you disable the setting, FortiGate advertises all prefixes in the BGP network table, regardless of the active routes present in the routing table. By default, the subnets under the config network command and the subnets redistributed from other routing protocols are advertised to all the neighbors. With a prefix list, you can be more selective about which prefixes to advertise to each neighbor. Additionally, prefix lists allow you to select which prefixes you want to use from each neighbor. In this example, we are creating a prefix list that allows the prefix 10.0.0.0/8, but blocks the prefix 10.1.0.0/16. By default, all the traffic that does not match a prefix list is denied. The prefix list is applied in the incoming direction from the neighbor 10.3.1.254. The local FortiGate applies this filter for all the prefix advertisements coming from 10.3.1.254. When applying a prefix list, all the prefixes that don't match an entry in the list are denied by default. This slide shows an example of a basic FortiGate configuration. In this case, remote AS is the same as local AS, which means it is an IBGP configuration. When implementing an RR, the configuration is done on the RR only. You can use the command shown on this slide to configure each neighbor that will be participating in the RR cluster. By default, a BGP route reflector propagates only one path for each prefix. If you enable additional path, a FortiGate acting as an RR can propagate multiple paths for a same prefix. This allows a more efficient use of BGP, while it can prevent suboptimal routing. ADVPN requires all the hubs to be configured as BGP RR. Additionally, scenarios where you want to combine ADVPN with SD-WAN requires BGP additional path. In those AD-VPN and SD-WAN scenarios, it is common to have multiple redundant IPsec tunnels between two locations. BGP Additional Path enables the AD-VPN hub to dynamically propagate all the redundant paths to each remote location through BGP. In this scenario, there are two redundant IPsec tunnels between Spoke 1 and Hub. There is also an IPsec between Spoke 2 and Hub. BGP over IPsec propagates the routing information. Hub is a route reflector with BGP Additional Path enabled. As BGP Additional Path is enabled, Spoke 2 receives two BGP route advertisements from Hub, one for each redundant tunnel. AD-VPN can use this routing to dynamically create on-demand IPsec tunnels between Spoke 2 and Spoke 1. In this section, you will learn about tools and tips for troubleshooting BGP. This slide shows a flowchart of the BGP neighbor states and how they change. Idle, initial state, connect, waiting for a successful three-way TCP connection. Active, unable to establish the TCP session. Open sent, waiting for an open message from the peer. Open confirm, waiting for the keep alive message from the peer. Established, peers have successfully exchanged open and keep alive messages. This slide shows the debug command you usually use first to get an overview of the BGP status and the status of all of its neighbors. This slide shows the local router ID and AS. For each neighbor, the output also displays the following: the AS, packet counters, how long the neighbor has been up. The last column is the neighbor state and number of prefixes. If the state is not established, this column displays the BGP state. If the state is established, this column displays the number of prefixes received by the local FortiGate from that neighbor. You can use the command shown on this slide to get detailed information about each BGP neighbor. The information includes peer IP, peer router ID, remote AS, BGP state, various timers, and message counters. The information also shows the number of prefixes announced and accepted, number of times that the session has dropped, and the last time it was reset. This slide shows the command you can use to get details about the prefixes the local router is advertising. Status codes identifies codes associated with a routing entry. For each prefix, the command displays the following: next hop IP, local preference, wait, AS path. This slide shows the command you can use to display the routes advertised by a neighbor. This slide shows the commands you can use to enable and disable the BGP real-time debug. Note that this example enables debug output from event and level information. The next two slides show examples of real-time debug outputs from the successful establishment of a BGP session. In this example, the output shows when the session goes to open sent state. This slide shows the real-time debug output containing the open confirm after the keep alive is received from the neighbor, as well as the establishing of the connection. The output also lists the prefixes FortiGate received after the BGP session is established. This slide shows how the command execute router clear BGP is used to restart a BGP session between two peers. You can also use this command to run a BGP soft reset, which forces both peers to exchange their complete BGP routing tables. Now FortiGate can log routing events, which enables you to get information that used to be available only when you ran the BGP real-time debug. By default, BGP event logging is enabled. You can disable BGP event logging by using the command shown on the slide. You can view BGP-related router events on the GUI. You can click any logged entry to view the details. Follow these steps to troubleshoot a BGP problem between two peers. Check that the local router can reach the remote peer. Check the TCP session. Check the BGP session. If the BGP session is established, check the prefixes received and advertised by each peer. This slide shows the objectives that you covered in this lesson.